In this video, we are going to discuss about magnetism. Well, magnetism is one of the branches of physics where we normally talk about electricity and magnetism. We can discuss how electric fields and magnetic fields interact and the effect they have towards each other. Now, for us to understand electricity and magnetism, it is important that we understand how to define magnetism. So in this video, we are going to explain more about magnetism and how to magnetize, demagnetize a magnet, and how we can store magnets. We are going to discuss about the types of magnets and so on. We are also going to discuss about the poles, the dipoles of a magnet, and so on. Now, let's start off. Now, as you can see here, magnetism is the ability of a magnet to repel or attract. Well, if a magnet can attract or repel, of course, repulsion only occurs in magnets only, and of course, a magnet can attract magnetic materials, as you are going to see in this video. So, the ability of a magnet to attract or repel is what we call magnetism. Now, we have types of magnets, and we are going to go through each one of them. We have so many types of magnets, but here we can discuss about a few of them. Now we have number one, U-shaped magnet is in a shape of a U, where the polarities are always at the end of the magnet. Now we have the north and the south are at the end, and therefore that we call it a U-shaped magnet. We have number two, a commonly known magnet which we use in the lab, known as the bar magnet. Is a bar where the polarities are at the ends. We have the south here and the north here. It's a very common magnet that we normally use in our daily lives. So we also have a horseshoe magnet, and this magnet is in the shape of a horseshoe, or the shoe of a horse, if you have seen it before. The polarities are at the ends, the south and the north. The polarities of any magnet are always at the end, except for the last type that we are going to discuss here, which is a ring magnet. It's a circular magnet, is in the form of a ring, but its polarities is not at the ends, but at the faces. So we have a circular or a ring. We have one face and the other face on the other side. Now the north and the south lie at the faces. So if you bring them close together, as we are going to see, something to do with the repulsion and attraction, something like that, or either attraction or repulsion might occur when you bring the faces of a ring magnet together. Now, we can also classify magnets in terms of magnetic and non-magnetic materials. As you can see here, we have magnetic materials. Now, magnetic materials are those materials that can be attracted by magnets. If you have a material that if you bring a magnet closer to it and it's attracted, that is defined as a magnetic material. We have so many examples, and one of the best examples that we normally discuss is iron. Now, if you bring iron close to a magnet, be it the north or the south pole, it's going to be attracted, and therefore iron is one of the best examples of a magnetic material. Now, we also have what we call non-magnetic materials. Now, non-magnetic materials are these materials that have the property of not being attracted by a magnet. So if you bring a magnetic or a magnet closer to a material and that material is not going to be attracted, then we are going to say that material is called a non-magnetic material. We have so many examples, and we are going to discuss how the poles or the dipoles or the properties of these materials that make them to be non-magnetic materials in our preceding part of this lecture. Now, the example is copper, wood, glass, plastic. So many of them, name them. So many materials have the properties of non-magnetic materials. Now we have what we call ferromagnetic materials, and these are the materials that are strongly attracted by magnets. So if you have a material that is strongly attracted by a magnet, then that material is known as a ferromagnetic material. The best example that we normally have is soft iron. Soft iron really is a material that can be attracted strongly by a magnet. and that is known as the ferromagnetic material. For us to understand better on magnetism, then it's important that we know the basic law of magnetism. Now, the basic law of magnetism states that if you have like poles, they repel. Now, we're going to discuss about the poles. Of course, the poles is just the north and the south. So if you have the north and the north, bring them closer together, they are going to repel, and that is known as the repulsion. And of course, unlike poles attract, if you bring the north and the south together, they are going to attract. And therefore, in general, we say that like poles repel and unlike poles attract in magnetism. That is known as the basic law of magnetism. Now also, we can discuss about the repulsion. Repulsion is the surest way to test polarity. And the reason is because, you see, if you bring a magnetic material close to a magnet, it's definitely going to attract, but it can never repel. So it's either if you bring a magnetic material close to a magnet, it's going to attract. It cannot be repelled, even if it is an unmagnetic material. And therefore, we normally say that repulsion is the only surest way to test the polarity of given magnets, because if you bring unlike poles together, they are going to repel. But at no time will you bring to a magnet close to a magnetic material and they repel. They cannot repel. They cannot repel. They have to attract or not attract at all. But a repulsion is the surest way of testing the polarity of a given magnet. Now, we also have what we call the properties of magnets. Now, the first property is what we call the magnetic strength. Now, it's important to note that the strength of a magnet lies at the poles. So at the end of a magnet, if this is a magnet, these ends are what we call the poles, the north and the south, or the south and the north, or the north and the south. They could be either depending on the magnet that you have. So the strength of those magnets lie on the poles, and therefore that's a very important property that we are going to learn. Now, we also have the direction of a magnet. Now, to understand about the direction property, you have to think of a magnet. If you have a magnet and you suspend it on air using a string, for example, and you just tilt it or disturb it, now it's going to move around and it's going to rest. It is going to rest at one point. Now, if you note the direction where it is going to rest, now, using a compass, you're going to notice that the direction is going to be north-south. A magnet will always rest in a north-south direction, a very important property. It will never rest on a southeast direction. Now, we also have magnetic poles. Now, the magnetic poles of any magnet lies at the end of a magnet. Now, if this is a magnet, the poles will never lie at the middle here. They are always going to lie at the end of that magnet. Now, a good example is if you have a magnet like this one and you break the magnet. Now, if you break the magnet, the two magnets are going to acquire new polarities. Now, for example, the magnet here is going to acquire a south here, so that we can have the south and the north for this magnet. Also, this one is going to acquire north, so that we have a north and a south for the other magnet. And therefore, it's important to note that the polarities of a magnet lie at the poles, or they lie at the end of a given magnet. Now, of course, that will happen even if we break this magnet here. We are going to have a south here, and we are going to have a north here, so that now for the two magnets, this is going to be a north, this is going to be a south, this is going to be a north, and this is going to be a south. And that can apply to any magnet that you might have. So that means the polarities lie at the poles, or at the end of any magnet. Now we have the attraction property, very, very important. And of course, we have defined in just a moment here that a magnet attracts a magnetic material. So it is important to note that the work of a magnet is to attract magnetic materials. If you bring a magnetic material close to a magnet, it's going to be definitely attracted, and therefore magnetic materials, or a magnet attracts magnetic materials. Now, after looking at the properties, let us now look at what we call magnetic field patterns. Now, what are magnetic fields, first of all? So magnetic field is a space where magnetic influence is felt. So we have a region in a magnet where a magnetic effect or a magnetic force is felt. That is where we call magnetic field. Now, if you have so many of them, then we are going to call them magnetic field lines. Now, the field is stronger at the poles. So the field is always stronger at the poles. So we said we have a north pole and a south pole for any magnet. Now the field is going to be very, very strong at the poles. And of course, we are going to talk about the properties, and we're going to really understand what we mean by that. Now, let's talk about the properties of a magnet, or the properties of magnetic field lines. Now, they originate from the north to the south. I think we have mentioned that before, that a magnetic field, or the magnetic field lines, will originate from the north going to the south, always. Now, the second property is that they are closer together where the field is strongest. So where the field is strongest, as we're going to see in our example here, the field lines are going to be really close together. And of course, lastly, they will never intersect or cross each other. So at no time will the field lines be intersecting with each other. If this field line goes through this path, this other one is going to go through this path, and they will never intersect each other. Now also, we can have the field patterns. From the properties we have said, they originate from the north to the south, and I want us to be able to know how to draw the magnetic field patterns for this magnet here. And we're going to have a field from the north to the south. Now again, this one is going to come from the north to the south. You have to indicate that they are closer together at the poles. If I can have a Alright, so the direction is from north, south, north, south. Now here, they are far apart away from the poles, but when it comes to the poles here, they are closer together. And that's how we can draw it. We can even have more here to show that this is the direction. We can have more here, and also here we can have more getting in the south from the north. So that's how we draw the field patterns. And as you can see from the second property, they are closer together at the poles and far apart in the poles, or away from the poles. Now in the second example, we have two magnets here. We have a north and a south here, and of course we're going to expect them to move from the north to the south. They are going to be closer together at the poles and far apart. So closer together at the poles, far apart away from the poles. And of course we could also have more moving from north to south, from the north to south. You can even add from north to south, and so on. So the direction has to be from the north to south. So we could also have a horseshoe. How do we draw the magnetic field lines for a horseshoe? Now this one is going to be, we're going to draw lines again from the north to south, from the north to south, from the north to south, from the north to south. The direction has to be shown from the north all the way to the south, from the north all the way to the south again. So that's how we can draw the magnetic field patterns of any magnet. So what happens when you have like poles? for magnetic field lines, as we have here, we have a north and a north. Of course, we know that the field patterns are going to move from the north to the south, so we are going to assume that the south is on this side, and therefore these ones are going to repel each other. We're going to have a field pattern moving in this direction. They will never cross each other, remember. So the direction is from north to south, north to south. Field patterns, they will never cross each other. The direction has to be that one. Very good. So we expect them to move. This region is a repulsion zone. So we are not going to have attraction. We are going to have repulsion of these field lines, and they always repel sideways. Now, if you have also a north and a south and a south, if you can have a south and a south here. If you have a south and a south, we're going to have, remember, it's always from the north to the south, and therefore we're going to have the field patterns coming in from the north to the south. So the direction is inwards. The direction is inwards. The direction is inwards. Remember, they are not supposed to cross each other, and therefore we are going to have a region here, the repulsion region. So we are assuming that we have a north somewhere here. They are going to come from the north to the south. Again, we are assuming that we have a south somewhere, and therefore they are going from, as if they are going to some north or to some south from this north one. So that's how we can do the field patterns for unlike poles. So generally, that is how we work out or we deal with magnetism. And in our next video, we are going to discuss more about the domain theory. Domain theory is what explains how magnets work, how we can magnetize magnets, how we can demagnetize magnets, and so on. So please remember to share this video, like, and also subscribe.